It's a pleasure to have our guest today, Professor Nico Cappelluti. Unfortunately, for reasons that we all know in these years, Nico couldn't make it to Rome, but we can at least have him remotely, and perhaps next time we can meet again in person. So just a little bit of introduction. Nico, he got his degree in astronomy from the University of Bologna in Italy in 2004. Then he got his PhD in physics and astronomy from the International Max Planck Research School in Germany in 2007. From 2007 to 2010, he was a postdoctoral scientist at MPE in Germany. From 2008 to 2015, he was also a visiting researcher at the University of Maryland, Baltimore County in the United States. From 2010 to 2015, Nico came back to Italy, to Bologna, and he was an INAF International Postdoctoral Fellow. From 2015 to 2017, he went back to the US and he was a prize postdoctoral fellow at Yale University. And then from 2018 to present, he's a professor at the University of Miami. Nico's research is focused on using wide field multi-wavelength surveys for finding observational proxies of the formation of supermassive black holes in the universe, determining the origin of the cosmic background, studying active galactic nuclei, their clustering properties, and also to investigate the nature of dark matter. So you can see that the research topics of Nico, they are very wide and extremely important. Today, Nico is going to talk to us about understanding dark matter and supermassive black hole seeds in the early universe, primordial black holes, and new missions. And in particular, Nico is also part of the science working group of the AXIS mission, which is a probe class mission, which is going to be proposed to NASA. So Nico, please go ahead.
Thank you, Francesco, for the introduction. And sorry for not being able to come to Rome. So there is no better times to talk about the early universe and especially about the first black holes than these days. So we have seen yesterday that we just underwent a major revolution in astrophysics with the first images and first science operations of the James Webb Space Telescope. And I really hope that what I'm going to show you today will be soon become part of the discussion, as I'm going to show you some theoretical predictions on what we might expect to see if the universe is actually the dark matter component of the universe is made by primordial black holes. Before starting talking about primordial black holes, I need to do an introduction so we can actually frame the problem of primordial black holes, not just like here is another dark matter theory, but why we believe that primordial black holes are a simple solution that might solve several difficult problems. Let me start from this famous plot that shows the spectrum of the cosmic X-ray background as measured by several missions, including the most recent work of my group with Chandra that measured the cosmic X-ray background between 0.5 and 10 keV. The cosmic X-ray background is basically the echo of the accretion onto supermassive black hole integrated over the cosmic history. And in fact, if you assume a a typical efficiency of, let's say, we call it epsilon, or but it can be something around 0.1, 0.1 for Schwarzschild black holes. The luminosity that we get out of black hole is nothing else than this epsilon factor times the sum of the accretion mass rates times c squared. This so basically the cosmic X-ray background tells us about how much mass has been converted into light across the cosmic history. This statement is also known as the Sultan argument. And in fact, we now know, thanks to Rosa, Chandra, and XMM Newton, that the X-ray background is not a background, but is just, I call it a technological background. It was a background when we didn't have instrument with optics sharp enough to resolve sources in point sources. And now we know that indeed the main components of the X-ray background were unresolved, mostly active galactic nuclei. And in this framework, all the populations of active galactic nuclei that we know today contribute to the X-ray background, with the bulk of the X-ray background produced between redshift 1 and 2. Above redshift 2 or 3, the situation is very unclear. If you look here on the right-hand side, I show how the luminosity, the density, the space density of quasars evolves as a function of their own luminosity, and we see that a very interesting trend where we have the most luminous, which are obviously the less abundant in the universe, peaking early in the history of the cosmic history, then low luminosity supermassive black hole. We call this trend downsizing, and it's probably related to how supermassive black holes interact with their host galaxy. But as you can see here on the right-hand side, the error bars are very large, and our knowledge of the cosmic evolution of supermassive black holes above redshift 5 is basically unknown. And here we see the deepest luminosity function ever measured for the X-ray selected AGN by Fabio Vito in the Chandra Dayfield South, and we see that we have a strong knowledge gap below 10 to the 43, and also at high luminosity we have very little sampling. Moreover, this luminosity function has been computed with very few points and in a very narrow survey. And basically, we have no reliable serendipitously detected X-ray source, serendipitous selected X-ray source, a redshift larger than 4, 5, and something. So basically, the epoch right before and after the reionization is completely unsampled. And in fact, if you look at the deepest images taken by Hubble, now kind of a piece for a museum with JWST, and the deepest images with Chandra, we have no idea of what are the progenitors of these supermassive black holes. And here is the problem. The problem is that we know how regular black holes, stellar black holes form from the death of a star, but we have no idea of how the biggest supermassive black holes form. We haven't observed the physics yet of the formation of supermassive black hole. We only have some clue. It is now then, it is this is the reason why it is of uttermost importance to access earlier epoch in the cosmic history, to start observing and measuring and characterizing the properties of active galactic nuclei in around and before the epoch of reionization, when we think the first black hole and stars started to shine. And here is another representation of the same problem. So here in this plot, you see on the x-axis the redshift from high redshift to low redshift from left to right. On the y-axis, you see the mass of a black hole, and here is the age of the universe. For the moment, don't consider this. And here, with this black dot, is the highest redshift quasar ever observed, ULAS J1120, that has been detected in the Sloan. Is a type 1 quasar, which is basically the only type of quasar that we are able to see that early in the universe. And you see that in the black line, and the mass of the supermassive black hole is around 10 to the 9 solar masses. This black line is the predicted evolution of the supermassive black hole. Is a backward projection of how the supermassive black hole would have grown if it was growing mostly at the Eddington rate. And you see that in order to explain this very high mass by 0.7 gigayear after the Big Bang, we need to go back around redshift 14, which is where and when dark matter halos are big enough to start trapping baryons. So basically, we see that we need to land in a region where these black hole seeds would have a mass of the order of 10 to the 5, 10 to the 6 solar masses, which is far above what we know from stellar evolution. So there is something that is not fitting our current knowledge of black hole formation. And so that's why we need to investigate what's happening in this history. On the contrary, here, I show what do we expect to see if we start from a putative seed mass of 10 to the 3 solar masses, and we make it grow at the Eddington rate for all this time. And as you can see, we can form a Sagittarius A star type supermassive black hole, but not a supermassive black hole that big. Obviously, we expect a redshift 7 to have a certain distribution of masses, so there might not be a single channel of formation of supermassive black hole seeds. And here in this talk, I want to especially focus on one possibility, that are the primordial black holes. Another thing that I want to show you here in this plot is are these three lines. These three lines is the flux expected from the flux limit of a putative X-ray instrument, 10 to the minus 17, 10 to the minus 18, 10 to the minus 19, and the line represents where this flux limit allow us to constrain the parameter space. And basically, it means that if we go down in the X-ray to something of the order of 10 to the minus 19 CGS, we are able to detect, that it doesn't mean that we will be able theoretically to detect supermassive black hole seeds of the order of 10 to the 5 solar masses growing at the Eddington rate. On the contrary, here there is a representation of what JWST might be able to do. And you can see that JWST in principle might go and find lower mass seed. The problem with JWST is the limited field of view, because as you've seen at the beginning, the space density of black holes sharply goes down at high redshift, and so we need wide field surveys to be able to actually detect these sources. So you are all familiar with the exercise that we do in the US every 10 years of going through the so-called decadal survey from the National Academy of Sciences. And basically, the community is tasked to provide inputs to a committee to identify what will be the most important topics for all the fields of astronomy in the next decade. And together with Francesca Civano, Ryan Ecox, and Becky Canning, we came out with with 3 bullet points that we believe are the future of the study of AGN demographics. And the first question is obviously, how did the first supermassive black hole form and grow so rapidly in the early universe? But on top of that, we want to know what is the census of growing supermassive black holes from cosmic dawn to the peak, the formation epoch, and beyond. And also, we want to know what is the influence of accretion to the growth of galaxies and large-scale structure and vice versa. So how do we do that? So the decadal committee came back with a suggestion to the institutions, the community, to open a call for probes, especially one X-ray imaging probe and one near-infrared imaging probe. And I'm involved in the AXIS probe proposal. I'm the chair of the AGN Science Working Group, and we are tirelessly working to come out with a compelling science case for this amazing instrument that will be, you can see this as an evolution of Chandra. So it will have one arc second on axis angular resolution, but the main advantage of AXIS is that because of its design, it will have very little degrading PSF with the off-axis angle. So if you go to 15 arc second of AXIS, you end up having 2 arc seconds of full width of maximum in your PSF, meaning that if you take Chandra, the average PSF on the field of view is about 5 arc seconds. The average PSF of AXIS across the field of view will be of the order of 1 point something arc seconds. So, and our goal is to keep the instrument between 1 and 2 arc seconds of angular resolution. It will have a very large effective area and a field of view that will be of the order of 24 arc minutes, but now we are discussing if having 36 arc minutes. It will fly in low Earth orbit and allowing low background, much less than Chandra. The PI is Chris Reynolds, and the deputy PI is Erin Cara from MIT. And the proposal is will be probably submitted sometimes late next year, after a call for proposal will be issued somewhere in the fall of 2023, with a goal to launch 9 years later, so between 2023 and 2032 and 2033. So, and here is what I told you. Here is the PSF versus off-axis angle that has been predicted by the people working on the optics compared with Chandra. And this is obviously a leap forward in terms of what we expect to do with surveys. The mirror technology is a lightweight voltage Schwarzschild telescope that takes advantage of commercial equipment and material. So basically, they use material and technology developed by the semiconductor industry and to benefit production of X-ray mirrors. So, and here it's basically what you see is that in order to do this mirror, you have several elements that need to be nested together and then put in meta shells and and then in a larger mirror assembly. So the point here is that we actually don't have produced a whole mirror so far, but the mirror has been tested in single pair modules and multiple pair modules. And basically, here is how the lab results are performing. If you take a single pair module measurement from 2017, we moved from having a 5 arc-second angular resolution to be sub arc-second. And now they started working on 5 pair modules, and they got something like 3 arc-seconds. But I know that the most recent measurements are already far below this, and we plan to match the expectation of Axis by the time of the proposal to be competitive for this call. So the technology is hard, but achievable. The focal plane is still under discussion if having either a hybrid CMOS or a digital CCD, depending on the performance that we need. We will come out with an idea, but the CCD will be fast readout CCD from MIT, or the CMOS will be made by PSU. So here you see that in this image you have a combination of the two types of detector, but we will eventually choose only one. Focal length is 9.5 meter, meaning that we will have a plot scale. If we go with 16 micron pixels, we will have a pixel size of something like 0.3 arc-seconds, which is more than enough to sample the PSF correctly. So the field of view is between 2 to 4 times the field of view of Chandra, and the response of the CCD is much more is at least twice the one of the Chandra ACEs. Also, the readout time will be much faster, so we'll have less problems with pile up. And here is the approximate effective area of axis in red compared with Chandra, XMM Newton PN only, and the theoretical Athena PSF. And as you can see that when you combine this with the superb PSF that we hope to have, it will have very high sensitivity on faint sources. These are simulations on what to expect to see with axis. Here is a simulation of about 1 square degree, and here is a zoom into a region on axis. So here you see what you see on axis, and this is a zoom to a region of axis, 8 arc minutes of axis, compared to an image of Chandra taken 8 arc minutes of axis. So you can see that axis will be much faster and sharper than Chandra to achieve deep exposures. And here is another core simulation with the galaxy cluster. So it will have also an outstanding sensitivity on faint diffuse sources. And we don't have actually an observation plan so far, but in order to achieve our scientific goals, we initially, at least for the extragalactic science, we plan to approach the science with the wedding cake strategy, going from a deep pencil beam survey, having an intermediate survey a la Cosmos, and a wide survey. And here is compared with Athena, and you can see where is the sweet spot for Chandra for axis in this game. And so, but the thing is, axis is still a PowerPoint mission. Can we do something now to have a look to what's happening in the early universe? Well, in order to have a look to what's happening at faint fluxes, until we have JWST, we can rely on the power of Spitzer and Chandra. So, and here in this image, you see the deepest image taken by Spitzer in the goods field. And once you mask all your sources and you Fourier transform your image, you see that you are still left with signal, and the signal is shows patterns in their fluctuations. And if you take the power spectrum of these fluctuations, you find that there is more fluctuations than what you would expect if the population of galaxies, if the cosmic infrared background was made only by galaxies similar to what we see at redshift less than 6. So people speculated that this excess in fluctuation in the CAB was actually due to the first population of sources. So what we propose is that if these sources are indeed the first star-forming galaxies, we should see also a burst of X-rays due to binaries, but also the first quasar that were shining at the same time. So we would expect a coherence between the cosmic infrared background and the cosmic X-ray background, and and in fact, if you look at the properties of the cosmic infrared background excess, we know that it's made by very faint sources, doesn't show any correlation with galaxies at wavelength shorter than 1 micron. So it's made by optically faint, and it might imply that these are sources with a Lyman break around 1 micron, so coming from redshift larger than 6. And it's consistent with being from high redshift sources. And then when we cross-correlate the signal with the cosmic X-ray background, we find a very strong cross-correlation signal, both when we cross-correlate the 3.6 and the 4.5 micron in Chandra with Chandra soft band. And here you see in this plot in black, you see the points, and in which is basically the cross power spectrum between the two maps. And here you see what you would expect in the cross power spectrum if the signal was made by known population sourcing, meaning by extrapolating the known luminosity function to fainter fluxes, both in the X-ray and in the IR, and we find an excess above 5 sigma between with respect to the model. So we try to speculate what this could be, and Angelo Ricarte, who is now a scientist at the EHT, was formerly a PhD student at Yale, did some back-of-the-envelope calculation, and we actually determined that if we want to explain our signal with black holes, you will need many more black holes than what the cosmic the Sultan argument tells. So here, in fact, in this plot, you see the accreted mass density, so the mass that is locked into black hole as derived from the quasar luminosity function, extrapolated up to high redshift, and here are the upper limits that we find. Basically, and in color, you see different seeding model of black holes. And the bottom line is that there are too few black holes in according to the Sultan argument to explain this cross correlation. But what if we don't need to satisfy the Sultan argument? So are all the local non-active AGN the result of non-active black hole the result of quasar growth only? But is there a population of quiescent black hole that have never accreted or they accreted very low? Well, in order to do this, we need to go and have a look to what LIGO has found. So basically, LIGO has found black holes that are more massive than what we have seen through electromagnetic interaction or predicted by stellar evolution. And there are certain particular pairs of black holes that are not consistent with this picture, but hopefully with the new run of LIGO we will get something more. And the other very interesting consideration is that if you look at this plot on the left, you see the distribution of the pre-merger spin of a group of gravitational wave events, and you see that they are mostly consistent with zero, which is not consistent with what we expect from stellar evolution. And then after merger, you see that then they pick up speed, which has been actually produced by the interaction itself. So, and this led to the oh, sorry. And on top of this, we have evidences of from Ogle of microlensing events from nearby objects that, if where stars would have been visible, but that are indeed dark, that have a mass of the order of around 1 solar mass. And here in the background, it's a prediction of one of the models that we use for primordial black holes. Keep that in mind for the next slide. So we have evidence of a possible population of black holes with about a solar mass or so mass in our Milky Way. And all this evidences basically resuscitated an idea of Stephen Hawking and Zeldovich and Chaplin and Bernard Carr back in the 60s, 70s, that actually predicted that black holes can form indeed in the Big Bang. And soon after the detection of LIGO, two main papers came out. One was from Simon Bird and the other one from Juan Bellido Garcia, that actually put the LIGO detection into the framework of primordial black hole dark matter, stating that indeed the results are consistent with all the dark matter being made by primordial black holes. And here is the history of citations and publications to primordial black holes papers and about primordial black holes paper. And as you can see, that LIGO basically made this field of the literature inflating. How do primordial black holes form? So we adopted the prediction of Juan Garcia Bellido, who made a very interesting model. Basically, what the model says that after the inflation, the universe is fluctuating and structure will eventually form. And the curvature in the early universe is very strong. Basically, everything is very close to be a black hole. The only thing that prevents structure to collapse is the high speed of sound. However, it turns out that during phase transition, the famous QCD phase transition, like the quark formation, electron-positron pion formation, you have a sharp decrease of the speed of sound, and this allows a fluctuation crossing the horizon to actually collapse into black hole. And every different phase transition that happen at different times of the universe happen at different horizon scales. And so basically, when a fluctuation crosses the horizon, the whole horizon collapses. And the earlier the formation of this structure happens, the smaller is the black hole. So basically, black holes that form earlier are the smallest one. And as soon as time goes on, we land into the most massive black hole. We can form even up to 10 to the 6 solar massive black hole late in the universe. And also, here is the mass spectrum that has been predicted by Garcia Bellido, 2019. And here you see that on the y-axis, you see the fraction of dark matter locked in black hole of a given mass. And the integral of this curve is actually 1. And you see that the spectrum shows 4 main peaks. The first one is produced by the formation of ZW boson and yields to planetary mass or asteroid mass black holes. The formation of proton and neutrons yields to the formation of this huge peak, which is just by chance next to the Chandrasekhar mass. The pion transition basically corresponds to the LIGO detected black hole around 10 solar masses, and then the electron-positron phase corresponds to the supermassive black hole formation. Now, I want to first to debunk a myth. All the limits that we have so far for primordial black holes as derived by lensing are wrong. And the reason is because all these measurements assumed monochromatic masses, mass spectra for PBHs. If you assume a broad mass spectrum from PBHs, then the lensing cross-section gets larger, and your limits on FPBHs, the fraction of dark matter in PBH, the given mass, go way up. And so here it's a slightly modified version of the previous mass spectrum to take into account the CMB constraints. So basically, they change a little bit the spectrum of the fluctuations, but still consistent with being starting from a Zeldovich spectrum. And here you see the whole mass function or mass spectrum of primordial black holes, all the way up to 10 to the 7. Below this, we don't actually believe it. And here you see the local black holes. So basically, the black holes form from the Sultan argument. So basically, you have a bunch of seeds of black holes at a certain point when halos have the condition to allow accretion. They start growing and resulting in what we see today. The interesting thing is that if you compare this mass spectrum with the with the density of intermediate mass black holes detected in the galactic center and Sagittarius A star-like black holes, this model really stays on top of the measurements. Now, the model does much more. So it's a very complicated model, and it involves some assumption and but also provides explanation. In particular, in this specific model, primordial black holes were invoked to explain the common origin of baryons and dark matter. Basically, when you have the collapse of a primordial black hole, you have the production of jets, and these TeV collision plus parton showers basically produce the interaction that allow to explain the abundance of dark matter and baryons and baryon to photon ratio. So this is basically what is behind the model. So this is hardcore particle physics. I don't want to jump into that. But this is the motivation behind this model. What do this? Let's suppose now for a moment, and let's believe for a moment in this model, and let's put aside all the cosmological debate, and let's assume that indeed the universe after the recombination comes up with this mass distribution in black holes. So we have evidences that dark matter and baryons leave after the recombination, move in the universe with a relative velocity, and the relative velocities of the of dark matter and baryons is shown here in this plot. But together with the streaming velocity, we have to take into account that the IgM carries as a temperature and as a speed of sound. So the actual velocity of the of dark matter versus baryons is given by this harmonic mean here of the relative velocity and the speed of sound of the IgM, and obviously C of S depends on the temperature and also on the ionization history. But in this plot, we have taken a standard ionization history. And the bottom line here is that basically these black holes, when they these primordial black holes are actually they are streaming in a flow of baryons. And we know, for example, from X-ray binaries that when baryons are flowing into black hole, we can have Bondi capture, and through the Bondi-Hoyle-Littleton capture, and this accretion and the accretion rate is basically inversely proportional to the velocity. And basically what you can see here, if the accretion rate is inversely proportional to the velocity, we have that the accretion rate onto this black hole should rapidly grow from redshift 1000 to redshift, let's say, 20. And then when the universe gets hotter, the velocity gets higher again, and then the accretion rate stops. So we should expect a peak of the accretion onto primordial black holes just from this stream around the redshift 20. And Günther Hasinger wrote a paper in 2020 tried to quantify what is the effect of this accretion to cosmic backgrounds, and as a byproduct, what he has shown, or here I have an error here in the slide. So what it shows is that if you assume that even this primordial black hole, while accreting through Bondi capture, if there is a non-large fraction of radio loud accretors, you can even explain the edge results, and the redshift where we see the peak seems to be consistent with what our model predicts. And here you see that it's enough a tiny fraction of radio background of a few percent in order to explain this feature in edges. Obviously, we need to first verify that the edges results are reliable, but so far we took that into account. And if you extrapolate the local fraction of radio louds to the early universe, we actually are able to explain this. And here is basically what is the summary of the results of what accretion onto primordial black holes might produce. So here you see the spectrum of cosmic radiation from the radio to the gamma. And what you see is that this accretion onto primordial black holes might produce a fraction of the radio background, a very tiny fraction of the cosmic infrared background, something like 10 to the -4, the cosmic infrared background, and something like 1% of the X-ray background, which is a lot. So, and then we decided to see if this black hole, this primordial black hole cosmology produce some nonsense in the history of galaxies, star formation, and basically we wanted to see how the universe would look like if actually dark matter is made by primordial black hole. What is the main difference between a lambda CDM and a PBH lambda CDM? So the main difference is that in a PBH lambda CDM universe, the dark matter doesn't behave like a non-collisionless gas, but is granular. So when you take the power spectrum of the mass fluctuations, here you see with no PBHs, the bottom line is the classic lambda CDM, and PBHs add, since they're granular, add a Poissonian component, which in Fourier space is just flat, and the amplitude of this component is basically proportional to the average mass of primordial black holes. In our model, where we have an average mass of the order of 1 to 10 solar masses, we have a very tiny increase of the fluctuation at very small scales. But this tiny increase of the fluctuation at small scales is large enough to allow an earlier collapse of the lowest mass halos. And here you see a comparison of the fraction of collapsed halos versus redshift for lambda CDM in dashed line and PBHs, PBH lambda CDM for halos with a virial temperature between 2000 Kelvin and 40,000 Kelvin, which are the halos where we expect the first stars to form. And so if you have a train high, now you will say, oh, wow, you have a huge amount of low massive halos. You should, of mini halos at low masses, you should have a huge amount of star-forming galaxies early in the universe. Well, the answer is no. And the reason is because when you combine this mass function, you have to make sure that the rotational velocity, the circular velocity of this halo is larger than the relative velocities between dark matter and baryons, so that baryons can be trapped. And it turns out that only a fraction of these lowest mass halos can indeed host star formation. But then we want to see actually how much more star formation we indeed have in a PBH lambda CDM universe. And we did it with an analytic model. Basically, we modeled the star formation rate with a modified press-injector. Basically, we compute press-injector mass function by simply adding the PBH component to the mass spectrum, and then applied a baryon to star conversion efficiency from the literature, and computed the star formation rate as a function of the halo mass and redshift. But then we found out that not all the halos, for several reasons, can form stars with a given with the same efficiency. So we have taken recent results from San and Furlanetto, where they actually modeled the efficiency of star formation rate with a function that depends on the halo mass. And these are the results. So we took our model and we ran a Monte Carlo by simply varying the escape fraction, the star formation efficiency, and the star formation efficiency and the minimum allowed star formation efficiency, and varied the IMF. So every color here represents 3 types of IMFs in the stellar populations that go from top heavy, that basically only pop 3, a combination of them. So, and we Monte Carlo'd our result by keeping as a reference the values of the between redshift 7 and 10 of the Madao plot, basically star formation history, and the Planck results on the ionization, because the more star formation you have, the hotter are your star, the more UV you have. So you have to make sure that you don't exceed the star formation. So if you want to have a universe like we see today, you can get there in a PBH lambda CDM universe in several ways. You can simply go straight as an extrapolation of the Madao plot, or you can go there through bumps of star formation episodes, which are due basically to the collapse of certain masses of halos. And also, we reproduce different types of reionization histories. So basically, here you see the Thomson optical depth versus redshift compared with Planck results, and you can see that we land into the Planck results through different patterns. The actual history of reionization is still a matter of debate, and several scenarios here might be constrained or interpreting this cosmology. But just by chance, I mean, one of the features of the PBH lambda CDM model is that the PBH dark matter, the halo occupation distribution of PBHs basically tells you that the number of black holes per unit mass black hole and unit mass halos is basically a constant, which is basically the fraction of dark matter that you have in a given mass, times the ratio between the halo mass and the black hole mass. So basically, you see that the halo mass and the black hole mass are by definition proportional in this model, and this is basically gives you a quick explanation of the M sigma relation. So basically, in a PBH lambda CDM universe, the M sigma relation is an intrinsic feature. So then we have taken our model and picked the halos where we have black holes larger than 10 to the 4 solar masses, make them grow, and then went to see how what is the luminosity function at redshift 6. Our model is the dashed model, and the straight line is extrapolate. No, vice versa. So our model is the straight line, and the dashed model is extrapolation from Vito et al. Compared with estimates from Rosita. Rosita doesn't have didn't detect serendipitously the sources are slow on sources, but we try to make a best estimate of our luminosity function, and it turns out that our predictions are not as crazy as we thought, by being consistent with other measurements and other extrapolation. In order to derive this luminosity function, we assumed a mass-dependent active fraction of around 2%. From Hassan et al. So basically, we have a function that describes what is the fraction of active galaxies per unit halo mass, and we assumed an SED derived from Fabio Pacucci, and assuming that basically most of the accretion is obscured, as we see in the in X-ray surveys with growth of the fraction of obscured AGN with the redshift. But we are also able to see with certain models to explain the excess in the cosmic infrared background, and here is the result of our model when added to foregrounds. And here you see how we decompose the flux production rate of the cosmic X-ray background as a function of redshift. You see this dashed line is EDAF accretion on PBH, is basically the Bondi capture accretion that gives you an EDAF spectrum. On top of this is the binaries X-ray throughput, which is basically obtained by the LX star formation rate. But interesting enough, what you see here is that our model, since requires halos to be requires halo that have enough baryon to produce AGN accretion, Our model predicts that we wouldn't be able to see quasars at redshift larger than 12 or so. But more interesting, we are also able to reproduce the cosmic X-ray background versus cosmic infrared background cross correlation. So, and for the future, since, as I told you, we have a slight excess of mini halos, it means that we have a slight excess of proto-galaxies. We went and computed the expected counts of sources at redshift larger than 7. And here you see the number counts, the function of the magnitude at 2.5 micron from our model here. And overplotted here, we have extrapolation from local luminosity function from Helgason et al. And here are the Spitzer S candles data from Matt Ashby. And here is the 10 kilosecond JWST limit. I believe that yesterday's images went somewhere like here. But what you see is that our model predicts a steep increase of the faint end of the luminosity function of star-forming galaxies at the faint end. So basically, and to summarize our model, we have a scenario where we have black holes floating in the IgM that are accreting via Bondi, and eventually these black holes collapse into halos. The most massive, the central black hole becomes the central AGN. We have star formation around it, and depending on the mass of the halo, we have different types of stars, and this basically is what we think is happening in the early universe if dark matter is indeed made by primordial black hole. So to summarize my results, the primordial black hole lambda CDM requires no new physics to explain dark matter and supermassive black hole seeds. PBH lambda CDM could explain the M-sigma relation as a direct consequence of the growth of primordial black hole dark matter halos. We explained several observational features, and we are consistent with observed star formation rates and Thomson optical depth. And we expect to have some feedback from JWST counts very soon. But in summary, the PBH lambda CDM universe would not look any different than a lambda CDM. It's just easier to model. Thank you very much.